Imagine inventing an unbreakable code, one that shrugs off errors no matter what the universe throws at it. That's the radical promise behind topological qubits, and it could change quantum computing forever. Let's start with the problem: fragility. Traditional qubits are like spinning coins balanced on their edge. The slightest nudge, a stray photon, a bit of heat, even a cosmic ray can knock them over, scrambling your data. Today's best superconducting qubits can only hold their quantum state for a few hundred microseconds before decohering. That's barely enough time to run simple algorithms, let alone anything groundbreaking. Here's the catch. To solve real-world problems, quantum computers need thousands, even millions of qubits working together. But if each qubit is this fragile, scaling up becomes a nightmare. You'd need massive error correction, which eats up resources and slows everything down. So, how do you make qubits that can stand up to the chaos of the real world? Enter topology. Instead of storing information in a single delicate state, topological qubits use the shape, the topology of their quantum state. Picture tying a knot in a rope. You can shake the rope, stretch it, or twist it, but as long as you don't untie the knot, the information stays put. That's the magic of topology. It's not about the details, but the overall structure. Now, let's talk about anyons and braiding. In certain exotic materials, particles called anyons can emerge. Unlike regular particles, anyons remember how they move around each other. Imagine braiding strands of hair. The pattern of the braid is what matters, not the exact path each strand took. In a topological quantum computer, you braid anyons to perform operations. The result? Errors from local disturbances, like a little tug or twist, don't mess up the computation because the information is stored in the braid itself. So what does this buy us? Fault tolerance at the hardware level. Instead of relying on layers and layers of error correction, the qubit itself is inherently protected. This could mean quantum computers that are not just powerful, but also stable and scalable, finally unlocking the promise of quantum advantage. But here's the reality check. Engineering topological qubits is incredibly hard. You need to create special conditions, like ultra-cold temperatures and precise materials, to coax anyons into existence. Microsoft, for example, has spent years chasing Majorana zero modes, a type of anyon, but practical devices are still in the early stages. The takeaway? Stability isn't just a nice-to-have. It's the key to scaling quantum computers from fragile lab toys to world-changing machines. If we can crack topological qubits, we might finally have the foundation for quantum computing at scale. The future of computing could be built on the strangest knots in physics.